China has carved a path through the Gobi Desert with a 2,700-kilometer railway, elevated on stilts across one of the planet's harshest landscapes. Temperatures range from 40 C in winter to 50 C in summer, creating extreme conditions for construction. Engineers confronted enormous challenges: shifting sand dunes that move meters each year, unstable permafrost that swells and melts seasonally, and a total absence of water across vast stretches. Conventional rail methods were impossible, forcing innovations like continuous overpasses, deep pile foundations, and specially coated structures to resist abrasion. This railway is a feat of engineering, connecting remote regions and demonstrating China's ability to overcome extreme natural obstacles. Why build the railway? Until 2010, Inner Mongolia, rich in coal, rare earth metals, and natural gas, was isolated by impassable roads. Transporting coal relied on trucks, burning a third of the cargo's value. Rare earth deposits, critical for electric vehicles and military electronics, remained inaccessible. The Bonobo region alone could supply China for 200 years. Recognizing this untapped potential, Beijing launched the Hohhot-Baotou Railway project in 2009, later expanded to link Beijing and Urumqi, forming a northern corridor to complement the overloaded southern route. The railway addressed three main goals: economic efficiency by lowering transport costs, logistical relief for southern routes, and political integration by connecting Xinjiang to central provinces. A single freight train replaced 300 trucks, reducing coal delivery from 4 days to 14 hours and cutting costs sevenfold. For passengers, a 250 km/h train reduced an 8-hour journey to just 40 minutes. The line had to endure extreme temperatures, sandstorms, and maintain precise schedules, far beyond European high-speed rail standards. Engineering challenges: nature versus technology. The Gobi Desert's terrain posed an unprecedented problem. Contrary to assumptions, the area is not a rocky plateau, but a mix of shifting dunes, salachaks, and permafrost, which swells into summer swamps. Conventional railways would fail. Even Soviet examples, like the Baikal-Amur mainline, were unsuitable for high-speed trains, where a 5 mm deviation risks derailment. The solution borrowed from the Beijing-Shanghai high-speed railway: continuous concrete overpasses on piles, leaving the track bed suspended above unstable ground. Temperature swings caused a 27-meter expansion along the line, so engineers installed special expansion joints every 32 meters, allowing independent movement while keeping the track smooth. Sandstorms presented another hurdle. Winds accelerated sand particles to 100 km/h, threatening structural wear. Engineers adapted aviation-grade coatings for jet turbines to protect concrete piles over 800 km of the route. Foundations in isolation. Piles 1.1 meters in diameter and 35 meters deep had to be drilled without roads, water, or electricity. Mobile diesel-powered rigs drilled 162,000 piles, autonomously operating for 20 days at a time. Cranes then installed prefabricated concrete spans weighing 1,200 tons, reinforced with steel fibers to last 100 years. Transporters with hundreds of wheels distributed the massive weight on soft sand, while custom stacker cranes installed spans with extreme precision. Seasonal constraints added complexity. Concrete cannot set below 5 C, and winter temperatures drop below 30 C. During frozen months, crews focused on metal structures, overhead lines, and cabling using heated electrodes in insulated tents. Shifting dunes were stabilized using straw mats and 12 million Saxaul bushes, forming a green corridor visible from space. Coordinating the desert. At peak construction, 24 assembly lines operated simultaneously. Satellite tracking monitored cranes, transporters, and drilling rigs in real time. Sections were completed at record pace, 256 meters per day per assembly area, far surpassing the English Channel Bridge benchmark. Approximately 180,000 workers lived in modular desert camps with dining halls, medical facilities, and power. Water came from deep wells or tankers. Diets were calculated for labor in low temperatures, providing about 4,000 calories daily. 48 medical teams ensured continuous care for the workforce. Infrastructure and technology. The railway features 45,000 overpass supports, traction substations, sensors, automatic traffic control systems, and 40,000 embedded sensors monitoring vibration, temperature, and concrete deformation. Special coatings protect the Solanchak River section from salt-induced corrosion. Each train consumes roughly 10 MW, with up to 30 trains operating simultaneously. The line costs 260 billion yuan, $36 billion, funded 40% by China's central government, 25% via Inner Mongolian regional bonds, and 35% through low-interest loans. Western analysts deemed it uneconomical, predicting a 70-year break-even. Chinese planners measured success by broader economic impact. Baonobo rare earth production nearly doubled, generating $4 billion in 5 years, while coal costs fell 18% in eastern China. Passenger numbers exceeded forecasts, transforming commuting patterns and raising local housing prices by 37%. Strategic and military implications. China's northern border, once a week's journey from central provinces, can now be reached in less than a day thanks to the new high-speed railway. This drastically improves the mobility of both people and resources in a region that was previously remote and difficult to access. The railway was designed not only for economic efficiency, but also with strategic and military considerations in mind. The People's Liberation Army participated in planning and reviewing the route, ensuring it could support rapid troop movements and logistical operations if necessary. Transport Minister Luxia Oping summarized the philosophy behind such projects. Infrastructure should not be evaluated solely on its ability to pay for itself, but on the opportunities and capabilities it unlocks. This strategic mindset is reflected in China's unprecedented investment in high-speed rail. Over 45,000 kilometers built in just 20 years, more than the rest of the world combined, demonstrating the integration of long-term planning, economic ambition, and national security priorities. Resilience in extreme conditions. In 2019, a Category 4 sandstorm halted highways and flights, but the railway continued, operating at reduced speeds with minimal delays. Trains were aerodynamically modified for crosswinds, with side skirts pressing them to tracks. Sensors automatically adjust train speed or stop service if winds exceed thresholds. Unexpectedly, the project created a new ecological corridor. Saxaul plantings attracted insects, which drew birds. Peregrine falcons now nest on pylons, hunting above trains. An unforeseen environmental impact. Impact on local communities. The railway passes through Inner Mongolia, near the independent state of Mongolia. Construction displaced some Mongolian herders, whose land was compensated below market value. Seasonal migration routes were blocked, forcing livestock losses. Language reforms in Inner Mongolia coincided with railway completion, prompting large-scale protests. Mongolia protested diplomatically, but lacked leverage due to economic dependence on China. At the border near Aranhat, Chinese and Mongolian rail gauges differ, requiring lifting trains and replacing bogies. China proposed extending its gauge to Mongolia. Mongolia refused, preserving its connection to Russia. Internally, the line achieved Beijing's goal of integrating remote regions efficiently. Global influence. China's desert railway has inspired international projects. India, Kazakhstan, and Saudi Arabia have studied the Gobi route, adopting continuous overpasses, fiber-reinforced concrete expansion joints, and satellite monitoring. By 2023, Chinese companies were building similar projects in 9 countries across 3 continents. Western observers view this as a strategic influence. Nations reliant on Chinese technology depend on China for maintenance and components. Hungary and Serbia are building lines to Chinese standards, bypassing European procurement rules. China's achievement is more than a railway. 2,700 km of continuous overpasses on 162,000 piles, 40,000 sensors, 12 million Saxaul bushes, and the coordinated effort of 180,000 workers. The Gobi Railway demonstrates that state planning can execute infrastructure deemed unprofitable, under conventional economic logic, with returns measured over decades. It is a concentrated example of China's technical, economic, and strategic ambitions, operational daily amid extreme desert conditions, sandstorms, and peregrine falcons hunting above.